Hello, good afternoon to everybody. Hello, respond please.
Good afternoon, sir.
Very good afternoon. Yeah, you see the all PDFs in your through WhatsApp? Are you received? Hello?
Yes, sir.
Okay, sir. Now, please wait for 2 minutes. 3 minutes more time. Please wait. Okay. Yesterday, we have explained here. Once again, good afternoon to everybody here. Now, this is the semester of mathematics, linear algebra. Yesterday, we have discussed subspaces and the algebra of subspaces and the linear combination and the linear span of a set and some other problems depends upon the linear span. Next, today we will discuss some other theorems and what is the linearly dependent and what is linearly independent of this part. Okay. Now, just you have to see here, if W1, W2 are any two subspaces of a vector space, then linear of W1 union W2 equal to W1 plus W2. Now, this theorem is also very important in the examination point of view. Just you have to see and refer. W1, W2 are any two subspaces of a vector space. Now, basically, union of the subspaces of linearity. The union of the subspaces of linearity means that is the linear sum. W1 union W2 is also referred as, this is the linear sum of the subspaces. This is the union of subspaces of linearity must be equal to the linear sum of the concept. Okay. Now that is L of W1 union W2 equal to W1 plus W2. We treat as the linear of union of the subspaces must be equal to the linear sum of the part. Linear sum means sum of the subspaces. Now, how to prove this theorem? First of all, basically, just you have to assume this one. According to the definition of linear sum, how to write the W1 of the vector? Here, the first subspace of the vector is say alpha 1. And alpha 1 can through the additive identity property, comparing it with the linear sum definition, alpha 1 plus 0 bar. Here 0 bar is also consisting W2. Means that is the second subspace of the element is 0 vector. Now that's why it can be written as alpha 1 plus 0 bar is also consisting W1 plus W2. Here alpha 1 is particularly belongs to W1 and 0 bar is also belongs to W2. So that's why here alpha 1 plus 0 bar means by B3 property, additive identity property, we are getting the values alpha 1 is also consisting W1 plus W2. So first of all, so let us assume that W1 of the vector, we are taking the W1 of the vector and it can be proved alpha 1 is consisting sum of the subspaces. That is the linear sum. So W1 is contained or equal to W1 plus W2. Similarly, W2 means alpha here 0 bar is belongs to 0 vector consisting W1 and alpha 2 belongs to W2. Therefore, 0 bar plus alpha 2. Therefore, is also belongs to W1 plus W2. Therefore, W2 is also contained or equal to W1 plus W2. Therefore, A contained or equal to B, B contained or equal to A. Therefore, this is here. W1 is contained or equal to, or W1 is a subset of some of the subspaces, and second subspace is also contained or equal to some of the subspace. Therefore, overall the union of the subspaces means W1 union W2 is contained or equal to W1 plus W2. That's it. Also, here any two subspaces means W1, W2, union of the subspace is also a subspace of sum of the subspace. Therefore, here union of the subspace of linearity, here that is the linear sum of the subspaces is a subspace of W1 plus W2. Again, let alpha is consisting sum of the subspaces And by definition of alpha, and also some of the values, we are taking alpha 1 belongs to W1 and alpha 2 is also belongs to W2. Therefore, alpha can be written as a linear combination of the vectors. Here, some of the subspaces is alpha 1 plus alpha 2. Now, particularly here, that is 1 into alpha 1. This is the linear combination. We can write as linear combination part of alpha 1 plus alpha 2. That is 1 into alpha 1 plus into alpha 2. So, just you have to observe here. Now we must observe here. This is the linear combination of the part A alpha plus B beta. Now A1 alpha 1 plus A2 alpha 2. That is the linear combination of that is an equivalent to the one of the vector. So this is the linear combination of elements of W1 union W2. So particularly alpha is consisting of union of the subspaces of linear. So that is the linear sum of the subspaces. Okay. We know that here the smallest subspace containing the union of the subspaces that is that must be contained are equal to sum of the subspaces. Finally, here A contained are equal to B, B contained are equal to A. Finally, A equal to B is here. So W1 plus W2, L of W1 union W2, L of W1 union W2 contained are equal to sum of the subspaces. That's it. Next theorem. Just you have to see and refer. If S is a subset of a vector space V of F, then prove that basically first of all here. Okay, S is a subset of a vector space. What is the vector subspace? Here, then prove that S is a subspace of V, L of S equal to here L of S equal to S. Okay, first of all, given the vector space S is a subspace, and second one, we are taking this one when the linear span must be equal to the subspace, subset of a vector space. Now this theorem is very important. Now suppose let S be a subspace of V. Okay, this is the S. First of all, we must assume that S be a subspace of V. Here alpha being any one of the linear span of the vector. Alpha can also be written. What is the linear span? To write as the linear combination of the part. That must be equal to the one of the vector space element. Now here alpha equal to summation AI alpha I. I represents 1 to m values. Okay, here all values, all field elements are scalars, and set of the elements, subset of the elements are vectors. Already that is the representative of vector space elements. Alpha 1, alpha 2, so on, alpha m. Now here S is a subspace of V. It is closely with respect to scalar multiplication and vector addition. So that's why here linear combination A1 alpha 1, A2 alpha 2, so on, AM alpha n. Here A belongs to alpha belongs to S, alpha being the vector. Therefore, at the same time, alpha belongs to S, and that same vector is also consisting the linear span of the part. Therefore, alpha belongs to L of S implies alpha belongs to S. Therefore, L of S contained are equal to S. And similarly, beta is also consisting some subset of the vector. Beta can also be written as 1 into B, 1 into beta. Oh, 1 is the scalar of the part. Therefore, this is the scalar multiplication. So, linear combination of the elements of S. Therefore, here beta be any one of the vector. That vector can also be written as can be rewritten as scalar multiplication of the part, and at the same time, this is the linear combination of set or subset of the part. So beta is consisting L of S, and S is contained are equal to L of S is there. That's enough. Therefore, finally, this is A contained are equal to B and B contained are equal to A. We are getting L of S equal to S is there. Okay. Suppose L of S equal to S. We know that. Already now the second one is replacing L of S equal to S. Now here second one is L of S. Now from the first part, L of S equal to S is there. Now we are getting the result is L of S. That is the simple part. Okay. Next theorem. If S and T both are subsets of a vector space, then S contained are equal to T implies L of S contained are equal to L of T. Now here S and T both are subsets of a vector space. Students, listen carefully. S and T both are subsets of a vector space. Now here S contained are equal to T implies L of S contained are equal to L of T. Second one, L of S union T equal to L of S plus L of T. Now here alpha belongs to L of S. Alpha can also be written as scalar multiplication. Alpha can be instead as the linear combination of the part A1 alpha 1, A2 alpha 2, so on, AN alpha n. All A values are field elements and alpha values are vectors. That is the subsets of the vectors. So S contained are equal to 2 means those field elements and those vectors also consisting is contained are equal to capital T, because already we know that S contained are equal to T. All the elements belongs to the S, and in the same manner it is also belonging to the capital T part. Because that is the subset of the vector space. Therefore, that's why here alpha is instead alpha can also be the linear combination of the finite subset of T. Here alpha is also consisting L of T. Finally, L of S. This is the L of S. L of S contained are equal to L of T is there. Second one. Here, this is the LHS and this is the RHS. S union T means now here L of S union T is vector is alpha. Alpha can also be written as linear combination of the part that to write as the subset of the elements alpha values, and T is the one of the subset of the elements beta values. To write the linear combination of the part, S union T means the sum of the elements of the subsets, finite subsets of the elements of the vectors. I alpha values and Bi beta I values. So that is A1 alpha 1, A2 alpha 2, so on AM alpha n. T values are B1 beta 1, so on B2 beta n. Okay, all A values and B values, those values are field elements. That is the scalars. Okay, that's why here all alpha A values given the subset capital S, and all beta values are belongs to the capital T. So, but AI values and those AI values belongs to L of S, and all the BI beta values belongs to the L of T. Finally, alpha equals to an elements of L of S and plus an element of L of T. Therefore, alpha is also consisting. This is L of S plus L of T. That is L of S union T is contained are equal to L of S plus L of T. Say this is the first equation. The same manner, we are taking at right side of the part, L of S plus L of T is the common vector is alpha. Alpha can also be written as L of S elements being the vector combination is gamma. L of T is the combination, linear combination of the elements is L is there. Now alpha is equals to gamma plus del. Here gamma is consisting linear combination of the part L of S, and del is also consisting a linear combination of L of T is there. Here gamma means linear combination of finite number of elements of S is there. That is L of S. And del equal to linear combination of finite number of elements of capital T. In a simple manner. Now here alpha equals to gamma plus del. This is the linear combination of finite number of elements of S union T. Because now those elements are is combining with the S and T is there. So that's why alpha equals to gamma plus del is consisting of L of S union T is there. So that is L of S plus L of T contained are equal to L of S union T. This is A contained are equal to B, or B contained are equal to A. Here A equals to B is there. Now this term is also very important, students. Now this is very, very important in final examination, those theorems, and you have to practice some other problems are also here. Okay. Now all those problems are also well practiced in yesterday. Okay. Next one. What is the linear dependence and the linearly independence? Listen carefully. What is the linearly dependent, linearly independent of vector? Now, first of all, E of F any vector space. Okay. Now, the vector space corresponding to one of the subset of the elements, those elements are consisting given in the vector space. Then the finite subset of the elements are alpha values, alpha 1, alpha 2, so on, alpha n. Okay. Now, these finite subset of vectors of B is said to be a linearly dependent. Linearly dependent set, there exists scalars A1, A2, so on, AN. That is A1 alpha 1 plus, A2 alpha 2 plus, so on, AN alpha n equal to 0. 0 part. Okay. But some scalars into 0, but not all 0. Again, first of all, to write the linear combination must be fed into the 0 vector. And that combination of the scalars not all 0, that is called linearly dependence. That is a very simple definition, because given the vectors, First of all, you have to write the finite subset of the vectors. That finite subset of the vectors of vector space is said to be a linearly dependent. What is the linearly dependent? Now, corresponding of the elements, field elements, then you have to assume then this, that is the scalars A1, A2, so on, AN. These elements are field elements, A1, A2, so on, AN. Okay, now to write A1 alpha 1 plus A2 alpha 2 plus so on, AN alpha n. When the linear combination must be equating to zero vector. Now, some scalars are zero, but not all zero. Some scalars zero, but not all zero. So, when the scalars are not zero, it's called the linearly dependence. Now, this is the basic definition, to the definition of the explanation. But in the same manner, a second method is also there. What is the second method? Matrices method. First of all, you have to write the those vectors to arrange the matrices form. Alpha 1, that is the first row. Second vector to write the second row of the matrix. And an alpha n to write the nth row of the matrix. So those vectors to arrange the matrices form to find the determinant of the path when the determinant of matrix, which is not when the determinant of the matrix must be zero. When the determinant of the matrix, when it is zero, that is called linearly dependence. That is the second definition of linearly dependence of matrices. Linearly dependence of vectors. Now, just you have to assume in the differential equation of the path. Okay, just you have to see it in the differential equation. Wronskian condition is there. Wronskian condition there. Let y1, y2, so on, yn of x. Those are all the solutions of given this expression. Okay, to write those solutions to arrange the matrices of the form to find the determinant of the path. Now, then their determinant of the solution of their path to require existence of the unique path. Because when the determinants of the solution, when it is when it is non-zero, that is Wronskian, W of y1, y2, so on, yn of x. When it is not equal to zero, that is called linearly independence. That is also comparing both is here when through the vectors and through the differential equations of the solutions. Now we have to assume the solutions. Now both are comparing it with the Wronskian and here through the linear algebraic linear elements. Now those vectors must be arranged as the rows in the matrices of the form to find the determinant of the matrix. Determinant of the matrix. So that determinant of the matrix, when it is non-zero, it's called linearly independent. When it is zero, it's called linearly dependence. Okay, now simple part. With the determinant of this part of the scalars, through the matrices form, when it is zero, that is linearly dependent. If it is non-zero, it's called here. That is called linearly independence of vectors. Now, basic definition is here, basically to the linear combination when it is an equating to zero part. All scalars are not zero. Okay, so that is called linearly dependence. Now each and every scalar must be zero. Each and every scalar must be zero. It's called linearly dependence. Okay, this is very simple conclusion. Okay, through the definition and matrices method. Okay, now just you have to observe here. Each and every scalar must be zero. Now that is called linearly independence by the definition. Independence of vectors through the definition. Okay, so that is the matrices of the form. Now those vectors, some finite subset of the vectors must be arranged in the matrices form to find the determinant of the matrix. When it is not equal to zero, that is called linearly independent. Now that is very simple expression for the definitions of linearly dependence of vectors and linearly dependence of independence of vectors. Thank you. Next one, see according to the definitions, we must derive some other theorems. We will explain some other theorems here. Now, first one, just you have to say here, every superset of the linearly dependent set of vectors linearly dependent. First of all, given the finite subset of the vectors is alpha 1, alpha 2, so on, alpha n. Those finite subset of the vectors to arrange the superset. That is the basic vector space of the finite subset is there. And to rewrite the superset is there. What is the superset of this part? And according to the set of vectors and x and some other vectors are also arranged given in the superset. So first of all, write the S is there. A alpha 1, alpha 2, so on alpha n. These set of vectors linearly dependent set of vectors. Linearly dependent means to apply the definition given in this expression here to corresponding the vectors to arrange the some scalars. That is, or those scalars are field of the elements. That's enough. Now this is A1 alpha 1, A2 alpha 2, so on An alpha n. Now those scalars not all zero because they are the given condition is linearly dependent set. Okay. So the linearly dependent means all scalars are not all zero. So to write the linear combination A1 alpha 1, A2 alpha 2, so on An alpha n equal to 0 bar. And here given the statement is linearly dependent vectors of the superset. Superset means yes, we have to assume, we must assume the S dash. S dash is the superset of given the set. Now all the set of the vectors and including the some other vectors are also to be arranged given in the set. It's called superset. Now alpha 1, alpha 2, so on alpha n and including beta 1, beta 2, so on beta n. Those vectors be a superset of set. Yes. First, now to arrange the linear combination according to this one A1 alpha 1, A2 alpha 2, An alpha n plus. Now superset of the vectors exceeding vectors 0 beta 1, 0 beta 2, 0 beta n. Here 0 and 0, these are all scalars are 0 in this linear combination of this part. Now, including the superset of the linear combination must be equal to 0 bar. Some scalars are 0, but not all 0. A1, A2, so on, An not equal to 0. So the given the superset is also a linearly dependent because including of the vectors given from the set, the finite set is capital S. So that's why superset of the linearly dependent vectors is also a linearly dependent. Therefore, that's very simple part. Next, second one, every non-empty subset of linearly independent set of vectors of the superset is linearly dependent. Not subset, subset is there. Okay. Second theorem, linearly independent set of vectors, then their non-empty subset is linearly independent. First of all, we must write the given the set of the linearly independent vectors. Alpha values, that is m consisting of the vectors given in S. Okay, that is the set of vectors is linearly independent set of vectors is set is denoted by capital S, and those vectors are alpha 1, alpha 2, so on alpha n. And let us consider the subset corresponding the values. Now in between 1 to m, just we have to assume up to k elements are there. We are taking only m k elements. That is alpha 1, alpha 2, alpha k. This is the subset of the path. Some elements given the set, some elements of the vectors to write the subset is there. Now k lies between 1 to m is there. So to write the k elements that is the subset of the S. Okay. Now to arrange the linear combination A1 alpha 1, A2 alpha 2, so on AK alpha k equal to 0 bar. Now to write the A1 alpha 1, A2 alpha 2, AK alpha k and exceeding of the elements 0 k, 0 alpha k plus 1, 0 alpha k plus 2, so on 0 alpha m equal to 0 bar. Now entire this is the linear combination finite set of V of m. So each and every one is 0, A1 0, A2 0, so on AK 0. So finally, given the subset is S is linearly independent set. So subset of the linearly independent vectors is also linearly independent. Superset of the linearly dependent vectors is linearly dependent. In the above here is there. Okay. Now don't forget two important conclusions here. One is the superset of linearly dependent set of vectors is linearly dependent. And the second one, A finite subset of linearly independent vectors is linearly independent. Now these two theorems, yes, it is completely depends upon the further expressions and the further theorems. Much more theorems are also elaborated here. Okay, next one. Students, listen carefully. Do you hear me? All are here? Hello? Please respond here. Hello? Can you hear me?
Yes, sir.
Okay, okay. Now, this is none other than term is a set of vectors which contains at least one zero vector is linearly dependent. Now, in your textbook, all those theorems given in the practice test, in the exercise part. So, we are just you have to available here. Now, all those proofs are available in this session. Okay, a set of vectors which contains at least one zero vector is linearly dependent. So, just you have to observe here, a set of vector means alpha, at least one zero vector. One zero vector means alpha 1 equal to 0 bar. Alpha 2, alpha 3, alpha m. Remaining all vectors are non-zero. Okay. Now we arrange the linear combination 1 into alpha 1 plus 0 into alpha 2 plus 0 into alpha 3 1 0 into alpha m. All scalars are all remaining second vectors alpha 2, alpha 3, alpha m non-zero, but one vector is zero vector. Here that is the primary vector is alpha 1. So alpha 1 equal to 0, a1 alpha to write the a1 alpha 1 equal to 0 bar, a1 is must be 1 is there because here the remaining vector is 0 bar, so automatically scalar is non-zero. So 1 into alpha 1. The remaining vectors are also non-zero and those scalars are 0 is there. So at least one scalar is 1, that is the field element, and the remaining all scalars are 0. Therefore, 0 bar means those scalars must be can also be written as remaining scalars. 0 bar, first one alpha 1 equal to 0 bar. Remaining vectors are alpha 2, alpha 3, 1, alpha m. So one vector is 0 vector, but remaining vectors are non-zero. So that type of set of vectors is also a linearly dependent set. So at least one zero vector given in this set, so that is also a linearly dependent. Okay. Now the next one, a single non-zero vector forms a linearly independent. At least single non-zero vector means to write the linear combination. So only non-zero vector to write the alpha being the one of the subset of V of F. Here V of F be a vector space. Then the subset of vector is say alpha. Here alpha is non-zero vector means alpha not equal to 0 bar. And the remaining scalar to write the linear combination with alpha. So A alpha equal to 0 bar is there. But here particularly A equal to 0 because through the non-zero divisors definition, the Rickson fields ring with the non-zero divisors, ring with zero divisors. Then the product is must be 0. One particularly one is 0 and the second one is non-zero. Okay, so particularly here alpha is non-zero and the remaining scalar must be 0 is there. So given the set is linearly. Okay, students, this is the problematic part. Particularly in examination, set of alpha is set of alpha is here given the set is with the alpha non-zero, so they given the scalar must be 0. So that given the set is linearly independent. So given the vector non-zero, given the vector is 0, scalar is non-zero. Scalar non-zero means that is the definition is linearly dependent set. Generated alpha, single vector generated A, okay, is a linearly independent set. Generated alpha is linearly independent. Okay, that's enough. This is okay. See the problems. These problems are very important. Now these problems are also just you have to see and refer in your textbook. In your textbook, only some problems are here. Okay, all the next after these problems. Now this is the end of this hearing. Okay. Show that the listen carefully. Now printing is very light is there, so there is no problem. When the subject when you must understand the concept, then automatically to achieve much more problems are here. Okay. Show that the system of vectors 1, 3, 2, 1, minus 7, minus 8, 2, 1, minus 7. Okay, 2, 1, minus 1. Now, these three vectors given in the set of the part, given the system. Now, this is the three-dimensional part. 1, 2, 3. This is the three-dimensional vectors. That is the V3 of part. It is linearly independent. So, first of all, by the definition one time, and second one is the matrices method. Just you have to see and refer. Three vectors is given. You write the three scalars A, B, C is there. This is alpha 1, alpha 2, alpha 3. A alpha 1 plus B alpha 2 plus C alpha 3 equal to 0 bar. You write the linear combination. You arrange the first coordinates of the elements. 1 into A plus B plus 2C equal to 0. Because 0 bar means each and every element is 0. Next one, 3A minus 7B plus C equal to 0. 2A minus 8B minus C equal to 0. There are three coordinates. These three equations must be solved here. A equal to 3, B equal to 1, C equal to minus 2. The given vectors are linearly independent. Okay, that's it. Second one, show that the system of vectors, there are three. Okay, this is the first method. When these three equations must be solved, when you are getting the scalars, those scalars are particular values, so that is non-zero. So given the vectors are linearly dependent through the definition. And the second method, you write this is the first method. Second method is matrices method. You write those vectors 1, 3, 2 first row, 1 minus 7 minus 8 second row, 2, 1 minus 1 that is the third row. Find the determinant of the part. Already we have practiced in lower level, lower classes to write down. Hello? Some other students are also here. Okay. To write down, to find the determinant of the matrices, these three vectors to arrange the determinant of the matrix. When the determinant of the matrix must be 0, now that is also given the set of vectors is linearly independent. Students, hello? Hello? Please note down carefully. Okay. That of each set of vectors, capital S equal to 1, 3, 2, 1 minus 7 minus 8, 2, 1 minus 7. That S means mod S equal to that of, first of all, we are taking the first vector is first row, second vector is second row, third vector is third row. To arrange, this is the determinant of the matrix. Mod of 1, 3, 2, second row 1 minus 7 minus 8, third row 2, 1 minus 7. Okay, find the determinant. Students, find the determinant. Okay, that determinant of the value is 0. Okay, so that is called given the system of vectors is linearly dependent. Okay, that's it. Now, by the theory, we arrange the some equations and to find the particular values of those scalars. So then we are getting the values given the vectors are linearly dependent. Second problem, show that the system of vectors 1, 2, 0, 0, 3, 1, minus 1, 0, 1. These three are vectors. Now, field of the elements are rational numbers. This is the three-dimensional vectors. Alpha, beta, gamma. Okay. These three vectors is linearly independent. Now, what is the Q? This is the field of rational numbers. Now, corresponding to the scalars, this is alpha, beta, gamma. Corresponding to the scalars means X, Y, Z. So, X alpha plus, Y beta plus, Z gamma. Z of gamma means minus 1, 0, 1 equal to 0 vector. To write the linear combination, that linear combination of the vector is equating to 0 bar. So we are getting the x plus x minus z equal to 0 and 2x plus 3y equal to 0 and finally 1 into y plus z equal to 0. When these three equations must be solved here, we are getting the values. Each and every scalar must be 0. each and every scalar is zero within the system of vectors is linearly independent. Very simple. Both are reversal. This is the one of the method by the definition. Okay. Next, second method is to arrange the matrices form. First row, second row, third row. Okay. Det of V3 of Q or det of A, whatever it is. Mod A or mod V3 of Q. Matrices form mod of 1 2 0 0 3 2 minus 1 0 1. What is the determinant of the part? That determinant is non-zero. Non-zero of the determinant is called linearly independent. The given system of vectors is linearly independent. That is the simple form. Now that is the second method. Next one, very important. Any two vectors, this is the third sum. If two vectors are linearly dependent, any two vectors are linearly dependent. Two vectors are linearly dependent means those scalars are corresponding scalars are not equal to zero. Corresponding scalars means A and B are corresponding scalars. That is non-zero. So to write the vectors are alpha and beta is there. Okay, that is the linearly dependent part. You arrange the linear combination A alpha plus B beta equal to 0 part. A alpha equal to minus B beta. Now we can prove that one of them is a scalar multiple of the other. One of them is a scalar multiple of the other. Now, by the condition is given the two vectors are linearly dependent and the corresponding scalars are non-zero. Therefore, A alpha plus B beta equal to 0 bar, that is the linear combination of part. Finally, A alpha equal to minus B beta, alpha equal to minus B by A of beta. Because A is denominator. Here A not equal to 0 means that inverse exists. So finally, alpha is a vector is multiple of the another vector. In the same manner, beta B beta equal to minus A alpha. Beta equal to minus A by B of alpha. Therefore, beta is the scalar multiple of alpha. That is the another one. Okay, this very simple statement. When the two vectors are linearly dependent, now then the result is one vector is a scalar multiple of the other. Here scalar multiple is minus B by A and here scalar multiple is minus A by B. That's it. Next one. Okay, just please write after two sums. Just you have to refer to your textbook is there. Now fourth problem is there are two vectors x1 y1 x2 y2. Okay, these two vectors are linearly dependent. When the determinant of the part, find the determinant x1 y1 x2 y2. Now the determinant is x1 y2 minus x2 y1 equal to 0. That's enough. x1 y2 minus x2 y1 equal to 0. So when the determinant is 0, then automatically condition is also given the vectors are linearly dependent. What about the condition when the vectors are x1 y1 x2 y2 are linearly dependent, then automatically x1 y2 minus x2 y1 equal to 0 is there. Next one. These are very important. These problems are very important. In the vector space Vn of F, n-dimensional vector space, the system of n vectors means already yesterday class. What is the usual basis? Students, very important. Okay. Now these classes are very important. Don't miss them. Because according to the subject, now you have to practice more than theorems. Okay, without consulting of classes. Okay. Now already one PDF is also dispatched in the examination point of view. That is the 73 pages material. Okay. Now according to this subject, according to this type of terminology, now you must effort enter the PDF. Okay. Next, just you have to observe here. What is the usual basis? V2 of F, two-dimensionality of usual basis is set of 1 0 and 0 1. V3 of usual basis. Please note down. Usual basis, ORR, regular basis, ORR, standard basis. Okay. The usual basis of V2 of F. the usual basis of V2 of F equal to set of 1 0 0 1. The usual basis of V3 of F. The usual basis of V3 of F 1 0 0. One vector is 1 0 0. Second vector 0 1 0. Third vector is 0 0 1. Set of 1 0 0 0 1 0 0 0 1. Okay, that is the second one. Okay, that is the second one. V4 of F or R power 4 of R, whatever it is. V2 of F, R square of R, V3 of F, R cube of R, V4 of F, R power 4 of 4 coordinates of the point. 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 0 0 0 1. That is the V4 of F. Finally, Vn of F means 1 0 0 1 0 0 1 0 1 0 0 0 0 1. This is the Vn of F usual basis or standard basis or regular basis. Okay. Now, these standard basis is always linearly independent. All standard basis, all usual basis, like all regular basis, is always linearly independent. Just you have to practice. Suppose we are taking the V2 of F 1 0 0 1 in the matrix part. AD minus BC 1 minus 0. We are getting the 1 not equal to 0. So that's why V2 of F is linearly independent. The same manner, V3 of F, that is 1 0 0 for first row, 0 1 0 second row, 0 0 1 third row. To find the determinant. Now that is also not equal to 0. So that's why that's enough. V3 of F in sometimes R cube of R is always linearly independent because that is the usual basis expression. What are the usual basis of V2 of F? In examination is given set of 1 0 0 1. What are the usual basis of V3 of F? 1 0 0 0 1 0 0 0 1. So in the same manner, Vn of F means set of 1 0 0 1 0 0 1 0 1 0 0 0 1 0 0 0 1. So A1 alpha 1, A2 alpha 2, An alpha n equal to 0 by the definition. So each and every scalar must be equating to 0. That's why this is called linearly independent. Okay, that's enough. So n-dimensional vector space is always linearly independent. That is the Vn of F expression. Now, in the same manner, very important problem. This is the sixth problem. Prove that the four vectors. What are the four vectors? Alpha, beta, gamma, del. These four vectors is given. According to these four vectors, now it is then we have to form the we must form the linearly independent set. But any three, we are taking any three, alpha, beta, gamma, or alpha, beta, del, or beta, gamma, del, or alpha, gamma, del. Any three is there, but it is linearly independent. Any four vectors for the given system of vectors is linearly dependent, but any three we are taking now that is linearly independent. Suppose A, B, C, D, these are all complex numbers. A alpha plus, B beta plus, C gamma plus, and D del equal to 0. Okay. Now A, B, C, D be the complex numbers. A alpha, B beta, C gamma plus, D del equal to 0 bar. Alpha equal to 1 0 0, beta equal to 0 1 0, gamma equal to 0 0 1, and del equals to 1 1 1. This is A plus D equal to 0. And according to the second coordinate, B plus del equal B plus D equal to 0, and the third coordinate C plus D equal to 0. So any three equations, these are three equations here. But suppose A plus D equal to 0 means A equal to minus D, and B equal to minus D, C equal to minus D here. Suppose D equal to minus K. For the first two value, D equal to minus K, A equal to K, B equal to K, C equal to K. So these values are substituting in the above expression, that is K alpha, K beta, K gamma, K del equal to 0. K must be the common. Now K value, K minus K del equal to 0. Now K is common. We are getting the values alpha plus beta plus gamma minus del equal to 0 bar. So when we are all scalars are not equal to 0, we are getting the given the system of vectors is linearly, system of vectors are linearly independent. So we are taking at least 3 is there, alpha, beta, del is there. That is then the linear combination is A alpha plus B beta plus C del equal to 0 bar. Those vectors are substituting given this expression. A is alpha is 1 0 0, beta is 0 1 0, and del equals to 1 1 1 is there. Now to write the first coordinates, A plus C equal to 0 and B plus C equal to 0, and next one C plus C equal to 0 is there. C into 1 equal to 0 is there. So when the C value is substituted in this one, B equal to 0, B and C values we are substituting here, A C value is 0, we are getting the value is A equal to 0. Each and every scalar is 0. So given the vectors alpha, beta, del are linearly independent. Similarly, we can show that any other three vectors are linearly independent. Either alpha, beta, gamma, or beta, gamma, del, or alpha, gamma, del, alpha, beta, del. Whatever it is, any three vectors are linearly independent. But given the four vectors are linearly dependent on the path. Yeah, this is the first method by the definition of this path. Okay. Now to practice the matrices method is also there. That is very simple. When the matrices of the determinant not equal to 0 means linearly independent, equal to determinant of the matrix equal to 0 for given the vector, for the given vectors, when it is 0, that is linearly independent. Okay, there is now easy conversation. Now the seventh problem. Okay, alpha, beta, gamma are linearly independent vectors of P of R. So that alpha plus beta, beta plus gamma, and gamma plus alpha, okay, are also linearly independent. So given the vectors alpha plus beta, beta plus gamma, gamma plus alpha, to write the scalars according to the scalars, to arrange the linear combination A into alpha plus beta, B into beta plus gamma, plus C is also one of the real number, and the field of the elements are also scalar. C of gamma plus alpha. 0 bar. Alpha, beta, gamma is common is there. Then alpha of A plus C plus beta of B plus what is that? A plus B. Gamma of B plus C equal to 0 bar. So alpha, beta, when the alpha, beta, gamma are linearly independent, those scalars are 0. A plus C equal to 0, A plus B equal to 0, B plus C equal to 0. By the given condition. So to write the A plus C means A plus 0 into B plus C equal to 0. This is A plus B. A plus B plus C is not there. The second scalar plus 0 into C equal to 0. Now in this section, B plus C is here. 0 into A plus B plus C equal to 0. You write the matrices of the form. You arrange A. A quotient is 1, 1, 0, 1. Second one, 1, 1, 0. Third one, 0, 1, 1. You write the matrix form. Okay. Now this matrix says, now this is the order of the matrix is 3 by 3. Rank of the matrix, rank of the matrices is completely dependent upon the order of the matrix. What is the order of the matrix? This is the 3 by 3. So then the rank, when the rank is completely depends upon the determinant of the matrix. Okay, so rank of the matrix is completely depends upon the order of the matrix. When it is determinant must be not equal to 0. So given the order is 3 by 3, so rank is 3 is there. That is very simple. This problem is also well practiced in matrices. Okay. Now, so each and every scalar must be 0. The only solution of the equation. So by the definition, the practice, each and every scalar must be 0. So that is linearly independent. But rank of the matrix, but the determinant of the matrix non-zero. So rank, the order of the matrix is 3. So rank is 3. So even the vectors are linearly independent. That's it. Now, the same manner, third problem is also the eighth problem is also same manner. Now, this is the ninth problem. Now, this is one of some different is there. There is no problem because in the matrices concept, the A, B, C or any three matrices is given. Okay. Now, these matrices are just you have to upload here. These are three matrices. Then their order is 2 by 3. There are 2 rows and 3 columns. Okay, and to arrange the linear combination, small a into capital A plus small b into capital B plus small c into capital C, because given the matrices is linearly independent. So to arrange the combination. So when the A, B, C are linearly independent means then their scalars must be 0. To write to substitute those matrices equating to 0 matrices for the order 2 by 3. So the first element 2a plus b plus 4c equal to 0. Second element, the first or second element a plus b plus 2c equal to 0. Okay, minus a minus 3b plus 2c equal to 0. Okay, the same manner 3a minus 2b plus c equal to 0. And the second row, second element, second row, third element. Now there are 2 by 3 means first row 3 elements, second row 3 elements. So those elements are equating to 0. All those equations must be solved here. We are getting the values. Each and every scalar must be 0. That's why within the matrices are linearly independent. Those matrices of the elements are vectors. Okay, that's it. Now, last one is very simple. For the complex numbers of the system is linearly dependent when it is 1 and I. When it is the set of vectors is 1 and I, those set of the vectors are complex numbers. So through the complex numbers of the system is vector space is linearly dependent. When the real number of the complex system, real numbers of the system is linearly independent. Real numbers of the system is linearly independent. For the given the set of vector is 1 and I, and complex numbers of the system of vector space is linearly dependent when the set is 1 and I. So minus I into I. We know that I square equal to minus 1, minus I square equal to plus 1. So here minus I comparing it with the linear combination A into I. A into from the A alpha. Here A value is minus I. So that is non-zero. So complex number is also non-zero. So the one vector is multiple of the other. So minus I belongs to C. So the set of 1 I is linearly dependent throughout the complex numbers. The set of 1 and I through the real numbers is linearly independent. That's it. Because A into I equal to 1. Okay, that's it. Okay, students. Now this is the main concept today. Now this is also one of the important theorem, the examination point of view. So that's enough. This is the final theorem in this class because next class is the 7th and 8th. Those 2 classes we will discuss some more important theorems and important problems. The examination point of view. Now this is the basic information and basic representation, especially in the especially to learn the linear algebra. Without these concepts, we can't achieve anyone. We can't learn in a number of theorems. Okay, we can't practice so many problems are here. Okay, now this is the end of the session. Now this theorem is also the completion of this theorem. Now this is the end of this session is there. Now if you have any doubt, please contact us and personal information. And already I will give the personal number is there. I have to give the personal number. That number is please note down my mobile number. 9989 4768 33. 9989 4768 33. Almost all the classes. Now this is the 4th class for English medium in linear algebra semester of mathematics. Now these 4 classes already we have present the PDF in the WhatsApp. Okay, please refer more than times. Number of times are also there. More than times, just you have to refer, see and refer, and watch the YouTube classes. Okay, thank you. Now, just see under the last theorem is there in this session. Remaining two classes, dates are in the new year, from the beginning of new year, 7th January, 8th January. Those two classes are last classes through online. Okay, and those classes I will present the more than problems, important problems in examination point of view. Okay, now there are much more subjective here. Quotient space, fundamental theorem of Riemann vector space. Every n-dimensional vector space is isomorphic to Vn of here. Okay, just you have to see and refer. This just through your material is there. Okay, just you have to see here. Now, this is the important concept. Okay. Just you have to refer. This problem is define vector space. Give example with briefly. Now, in this examination, very important. Okay, this is very important. Next one, define finite dimensional space. Basis of a vector space. Prove that V of F is a finite dimensional vector space. Then there exists a basis set of V. This is one of the problem. Now, just this is the definition of a vector space and finite dimensional space definition, basis of a vector space definition. And then after that, existence theorem is also represented here. Now, according to these classes, you have to see and refer define linear span. And one of the theorem is also given here. Now, to practice this theorem is also here. This is also one of the PDF the examination point of view. Now, much more important, much more useful in the final examination. Okay, now this is the one. Now this is the quotient space. Now we will discuss the next class is the quotient space. Okay, now rank and nullity theorem. These are very important concept. Now, define singular transformation. Okay, now this is also linear transformation presentation, define singular transformation, non-singular transformation, and according to those definitions, then you have to prove that a transformation is an isomorphism if and only if it is a non-singular. It is a non-singular. Now this theorem is also very important. Okay, we will explain the next further session. Now this is one of the important theorem in matrices, that is the Cayley-Hamilton theorem. Without this theorem, we can't expect the question paper. Now state and prove Cayley-Hamilton theorem. Now this is the matrices part. Okay. Now this theorem is Cayley-Hamilton theorem means one of the important theorems. According to this theorem, and proof is also very important. State and prove the Cayley-Hamilton theorem, and using this theorem to practice to find the characteristic values and characteristic vectors. Now these are all problems. Now without this one, we can't expect the paper. Now, this is one of the important theorem, Gram-Schmidt orthogonalization process theorem. Gram-Schmidt orthogonalization process theorem. This theorem is also very important in the final examination, and according to this, problems are also practiced here. Okay. Now, this is the according to the matrix. The matrix is given to find the characteristic roots and the characteristic vectors when they given the matrix. Okay. Next class we will explain. Is very clear. Okay. Next one, define inner product space, state and prove Cauchy square inequality. Now, this is the fourth block, inner product part. So, what is the definition of inner product? And here, the one of the theorem is Cauchy square inequality. This theorem is also very, very important, and this is the linear transformation problem. So, one question is three blocks are there. 1, 1, 1, 2, 1, 3. There are three questions in the first one question is found here. Okay. Now, this is the complete information and the final examination of this part. Okay, students. Now, those theorems, Cauchy square inequality theorem is this. Without this theorem, we can't expect the question paper in the final session. Okay. Okay. Next, some theorems are also just you have to provide here. Okay. Now this is the necessary and sufficient condition of subspace theorem. Okay. Now this is the transformation problem. Okay. This theorem is very important. The theorem is every n-dimensional vector space is isomorphic to n tuples of the field elements. Okay, now these theorems are also explained here. Please wait. Now in the further session, that is the 7th January and 8th January, these theorems are completely explained. Try to my level best. Okay. Now almost all already the PDF is given here, is in your under. Okay, just you have to see and refer in your WhatsApp group. Find the null space. This is the transformation problem. Transformation is given. Find the null space, range, rank, and the nullity of transformation. Okay. Next, in the same manner, these are all transformation problems. Okay. So now, just see and here, these are all matrices problems. And orthogonal and orthonormal. This is the fourth block. This is the triangle inequality, parallelogram law. Now these theorems are very important in the final examination. State and prove triangle inequality, state and prove parallelogram law. Now these theorems in the fourth block is in your textbook. Okay, these are. Okay, next one. Just you have to see and refer. This theorem already you have to previously explained this problem. Show that the four set of the 1 0 0 0 0 1 0 1 0 0 0 1 1 1 1. This is the basis of V3 of R. According to the four vectors are linearly dependent. Any three vectors are linearly independent. Just recently explained here. Okay. Next one. V of F. What is the finite dimensional vector? Just to see this theorem. According to the theorem, first of all, what is the finite dimensional vector space? Now, from the definition of dimensional vector space and the finite dimensional vector space, we will show that and we will prove that the any two bases of finite dimensional vector spaces have the same number of elements. Now, this theorem is also very, very important. That is, this theorem is also called invariance theorem. Without this theorem, we can't expect in the final paper. Okay, the examination of the final session. Okay. Yes. Now, in the next class, we will explain the invariance theorem and what is the basis of a vector space, what is the dimension of a vector space, and some other theorems on dimensions, finite dimensional part. Now, dimension of W1 plus W2 equal to dimension W1 plus dimension W2 minus dimension of W1 intersection W2. This is the sum of the subspaces of the dimension theorem is there. Next, quotient space. And quotient space theorem is dimension of V by W equal to dimension V minus dimension W. These two theorems, and this is the invariance theorem and basis extension theorem. These theorems are very, very important in the vector space part. And rank and nullity theorem, now that is also one of the important theorem on linear transformation. Okay, before the theorem, what is the linear transformation and the properties of linear transformations, and every n-dimensional vector space is isomorphic to n-dimensional vector space. And at the same time, fundamental theorem of homomorphism on vector spaces. Now, these are all very important theorems, important theorems in the linear algebra, in the first block and the second block. Okay, students, next class we will meet again. As usual, same timings. Now, just you have to see and refer and much more practice in the previous classes. Any doubts? We must contact as a personal number. Okay, thank you one and all. Already time is over. There is no more than 2 times are also over. Okay, 2 minutes are also extended here. Anyhow, any more any doubts are here? Friends, please ask here. Please asking. Any doubts? Hello? Any doubts? Okay, thank you one and all. Wish you all the best and wish you good luck.